Hello everyone, I'm back with the second part of the video on climatology as promised. So let us begin. So in the last part we had seen the calculation of solar constant, the predicted temperature of the earth, the actual temperature of the earth, and we proved that how greenhouse effect is important for us. Now that we were doing the studies on the uh, insolation and heat budget, so let us start today with the distribution of insolation. So as I had already told you all that insolation is the incoming solar radiation. So if you look at this picture over here, it states the curve for the insolation with the changing months. These are the months and this is the insolation in watt per meter square, and these lines they indicate the various latitudes of the northern hemisphere. So for the sake of simplicity, first we will discuss the northern hemisphere and then we can transpose those results over the southern hemisphere as well. So if you look here carefully in this first plot, you can see that this is the month January to December and the insolation distribution is given. Four important events are marked. They are the equinox, the two equinoxes, the and the two solstices. So I am sure you all are aware about the equinoxes and solstices. The equinoxes are those times of the year when the day and night are of equal length, while the summer solstice is the one in which the day is the longest, and winter solstice the night is the longest. Now if we try to understand this, so we can see here that in the month of January the maximum insolation is received at the equator. So you see here January, and this blue line is of the equator. So maximum insolation is received at the equator, followed by the 30 degree, that is the tropics, then the 60 degree, that means the high latitude. So during the winter months we can see here that the uh, insolation, it is maximum at the lowest latitude and least at the higher latitudes. As we move ahead towards the other times of the year, so during the equinoxes the situation remains the same. Equator has the highest insolation, followed by the 30-degree latitude, then 60 degree, and then the poles. As we come to the June solstice, that is the summer solstice, a very interesting thing happens over here. We can see here that 30-degree latitude, this 30-degree latitude uh, is receiving higher amount of insolation than the equator. Interestingly, the polar latitudes, the north pole is getting the highest amount of insolation during the June solstice, which is also called as the summer solstice, and it is followed by 30-degree latitude, then 60-degree, and equator receives the lowest amount of insolation during the summer solstice. As we reach towards the uh, September equinox, the same situation as the March equinox happens, and during the winter solstice, then the situation then returns back to equator, followed by 30, followed by 60-degree latitude. Now this interesting phenomenon happens over here due to the position of the earth during the solstices and due to the tilt of the earth. So time and again we will discuss this, that tilt of the earth is a very important factor. Now uh, let me just draw a diagram for you over here. Let me draw this diagram for you, wherein I'll try to show you the position of the earth during the different times of the year. So let us imagine that this is the sun. Okay, and we all know that the earth goes around the sun in an elliptical orbit. Okay, now the winter solstice, this is the earth, so this is winter solstice, and this solstice happens during December month, most probably 21st December. Then we come to the equinoxes. This is the March equinox, also called as the vernal equinox. The vernal equinox, it occurs on 21st of March. Then the earth comes to the summer solstice, and it happens on 21st June. Most of you would be aware that uh, India celebrates the International Yoga Day on this date. This is because on this date the uh, day is the longest. And then we come to the other equinox, that is the sept sorry that is the September equinox, also called as the autumnal equinox. And the date on which it occurs is 23rd of September. So if we look at these four positions, they are very important in as regards to the insolation coming on the earth. Now you should remember, sometimes this question is asked uh, about the positions. So let me just tell you a few interesting facts over here, that from vernal equinox to summer solstice, the total time taken is 92.8 days. Okay, from summer solstice to autumnal equinox, the time taken is 93.6 days. From autumnal equinox to winter solstice, the time taken is 89.8 days, and from winter solstice to vernal equinox, the time taken is 89 days. So you should keep this in mind, these four positions and time taken by the earth to reach from one position to the other. Now this is a very important fact that you all should remember. Now let us come back to the slide. So I just drew this diagram. Now going back, see, if we see here, during the summer solstice, what did we see? That poles, they received maximum amount of insolation, followed by the tropical latitudes. So why is this happening? Due to the tilt of the earth, we can see that the north pole during the time of summer solstice is having day of 24 hours. It means, so when there will be daytime, then the solar insolation will constantly be coming over there. Even though the poles receive lesser amount of insolation, but due to the longer daytime, their insolation becomes the highest. But if you see here carefully, I'll discuss this in more detail in later slides. If you see here carefully, that during the summer solstice, the equator is no more receiving the maximum insolation, because it is during that time the tropic of Cancer, that is 23.5 degree north latitude, receives the direct sunlight. As a result, the tropical latitudes, they receive maximum insolation. So the longer duration of daytime on the poles makes it to receive highest amount of insolation, followed by the tropical latitudes which are in direct contact with the sunlight due to the tilt of the earth, followed by the 60-degree or the Arctic Circle region, and then the equator. So this is the reason that the distribution of insolation goes this way. So if in the second plot you can see here how the northern hemisphere and southern hemisphere, they vary in their insolation distribution according to latitude, and the annual average distribution is also shown here. So during the summer solstice and winter solstice, during the summer solstice we can see that the northern hemisphere, it gets the maximum amount of insolation, but during winter solstice, if you can see here, now the north pole is getting a night of 24 hours, night of 24 hours. As a result, see, the insolation is 0 uh, for this latitude. The insolation during the winter solstice is 0. Okay, moving ahead. So I hope you will remember this diagram. There have been a few questions asked over this four positions. Now imagine that the earth was not tilted. अगर अर्थ टिल्ट नहीं होता, if the earth was not tilted, then what could have happened? The equator would have received direct sunlight. It would have been the location with maximum heat. So highest temperature means the lowest pressure. So the winds would have carried this heat from the equator. So the winds would have been moving from equator to poles, and from the cold regime would have been here like this. So the warmth would have gone in one direction only, and the cold winds would have come over here. But we all know, and due to if the earth was not tilted, this question has been several times asked in the examination, what would have happened if the earth was not tilted? If the earth was not tilted, we would not have seasons. We would not have seasons. We would not have had wind belts. Wind belts, because in that case only there would have been two directions, from poles to from equator towards poles, and then from the poles towards the equator. But we all know that the earth is tilted, and since the earth is tilted, then we can see here that during the summer solstice, what I had explained previously, during the summer solstice we can see here that this solar insolation, the solar rays, they come and they hit this 23.5-degree latitude at an angle of 90 degrees. And from this latitude, if we go towards the poles, we can see here that the rays become slanting, वो टेढ़ी होने लगती हैं, and their angle decreases from 90, then 47, then 23.5, and then over here. And if we go southward at the equator, the solar insolation is not perpendicular, rather it is at an angle of 66.5 degree. So during summer solstice means during this position, 23.5-degree latitude or the Tropic of Cancer basically acts as virtual equator. So now here the Tropic of Cancer acts as virtual equator, and it contracts the maximum amount of insolation. So uh, then that was the reason that we got the latitudinal distribution like this. As we go from Tropic of Cancer towards the Arctic Circle, we can see the amount of uh, insolation decreasing because of the slanting rays. But here an interesting fact is that the poles, the polar latitude, will have a daytime of 24 hours, which means longer time is available to store the heat, and therefore the insolation it's received at the poles during summer solstice in the northern hemisphere will be the maximum. I hope you all understood that why this latitudinal distribution is like this. So if you get a question which of the following gets the maximum amount of insolation during the summer solstice, answer will be the North Pole, not the equator, not the Tropic of Cancer. Keep that in mind. Okay. All right. If we look at the winter solstice, now the situation is the same, but just one thing over here is that now the North Pole is away from the sun. At this position, the North Pole is away from the sun and it will be having a 24 hours night time. Rather, the Tropic of Capricorn now acts as the virtual equator and it is getting the maximum amount of heat. So the same thing over here will be acting. So during winter solstice, that is the December solstice, you can see that the insolation received at the North Pole is 0. Maximum is at the uh, equator over here, followed by the tropics and then the 60-degree latitude. So this during the winter solstice, the situation changes for the northern hemisphere. We are not talking about southern hemisphere in this case. This is winter solstice condition for the southern hemisphere. So here, if we look at this this zone, then equator will be having higher insolation than Tropic of Cancer. It will be having higher than Arctic Circle, and it will be having, and the poles obviously will have 0. So if a question is asked during winter solstice, which latitude receives the maximum amount of insolation in northern hemisphere, answer will be equator. Keep that in mind. Okay, and this is the reason why. All right. So, as the insolation, the solar insolation or solar radiation starts coming on the earth, then there are several factors that deplete the solar radiation, because the solar radiation has to cross the atmosphere. And then there are four major factors which cause the depletion of solar radiation. The first one is the scattering of light. The scattering of light, a very important fact over here is that light will be scattered by those particles which have diameter diameter less than the wavelength of the radiation. So the dust particles, the fine atmospheric particles which are smaller than the wavelength of the incoming radiation, they scatter the light. While when the diameter of those particles is greater than the wavelength, then they will cause the diffusion of the radiation. So uh, the water droplets, the water vapor, it has the diameter more than the wavelength. It will cause these lights to diffuse, while the finer aerosols, they are smaller in size than the wavelength, they will cause the light to scatter. So once the light is, suppose that this is the sun, it is sending in radiation, and these are the particles, aerosols, which will cause scattering of light. They will not allow the 100% light to come on the earth, then definitely its amount will be lesser. Similarly, when they diffuse through the clouds, the amount also gets depleted. Third is absorption. Absorption is a phenomenon in which the atmospheric entities, uh, they retain the radiation, and then they convert it to different form of light, different form of energy, that is called as absorption. So when the light, the visible light comes through the atmosphere, it is absorbed and then it is converted to long wave infrared emissions. So that is one of the ways how the solar radiation gets depleted in the atmosphere. And the fourth one is the reflection. We all know that sometimes when the light hits a surface, then some part of it is reflected back also. So the atmosphere reflects back the light, clouds reflect back the light, earth's surface reflects back the light, snow reflects back the light. So this phenomenon of reflection of light is also referred to as albedo. Let us see what albedo is. Albedo is basically reflectivity of light surface by a surface. So if we see here, fresh snow has the highest albedo. Keep that in mind. It has the ability to reflect back almost 85 to 90% of the light falling on it. Similarly, clouds have very high albedo. Then water has very less albedo. Ice without the snow has around 40% albedo. So this is the amount of uh, radiation which is reflected back. So if we see here, other than snow and ice, clouds, they have the ability to reflect back the light. Also, if we look at the latitude, so if remember, if in any graph or any plot, latitudes are written as positive, they mean northern hemisphere; negative, they mean southern hemisphere. So in this you can see how the albedo varies with the latitude. So if we see here, then the north pole and south pole, they show maximum albedo, followed by the decreasing value as we go towards the lower latitudes. So keep in mind, the average albedo of the earth is 0.30. I had told this to you in the previous video. So albedo plays a very important role in deciding the total amount of insolation received. I'll give you a very common example. So let us say you go to Manali or Gulmarg or Srinagar, where a lot of fresh snow has fallen, and on a sunny day, if you stand over there, you will get face burns because the amount of light being reflected by that snow is too harsh for you to bear. That is why people in who are doing skiing and all, on a sunny day, they wear goggles to protect their eyes from that scorching light that is coming in. Okay, so albedo is a very important factor. So it means that, taking in account these four factors, scattering, diffusion, absorption and reflection, we can safely presume that the total amount of solar radiation coming on the earth is not the same as sent by the sun, because these four factors, they reduce that amount. So if we consider if in all those factors, then we get what is called as the heat budget of the earth. What is heat budget? We all know one thing, that the amount of solar radiation received on the earth, absorbed on the earth, and the amount of radiation sent back to the space by the earth, they should be equal. Only then we will have this heat budget in place. So this diagram I have taken from DS Lal's climatology book. He has very nicely explained this. You should read this diagram from that book also after I explain. Imagine, now see this diagram. Let me add a new slide to it, and I will explain this to you once more, so that, okay, let us imagine. Now see this. This diagram has two parts: the total solar radiation that is coming on the earth, and outgoing long wave earth radiation that is going back into the space. So let us now consider first this part, these solar radiation coming on the earth. So let us imagine that sun has sent 100 units of incoming solar radiation. 100 units of incoming solar radiation. Out of this 100 units, you can see around 34 units, it is immediately returned to space. Okay, so out of the 100 units that come on the earth, 34 units energy returned to space. Okay, so here, out of this 100 units, 34 units, they are immediately returned to space. Return to space. Now, out of this 34 units, we can see here that 25 units it is reflected by clouds. Okay, the first mechanism, that out of those 100 units, 25 units is reflected back by the clouds. Around 2 units it is reflected back by the earth. Okay, earth's surface, it reflects back 2 units, and 7 units is reflected by the sorry, not reflected, 7 units is scattered by the atmospheric particles. Okay, so out of this 34, we have 25 units re, uh, reflected by clouds. So clouds reflect these 25 units. 2 units reflected by earth's surface, earth's surface, and 7 units they got scattered. Now, what is the total amount of solar radiation remaining that crosses the atmosphere? We have now only 66 units, which enter the atmosphere, enter atmosphere to reach the earth, enter atmosphere to reach the earth. Now, see this. Of, uh, of that 66 units, 19 units are absorbed by atmosphere in clouds. So of these 66, 19 units absorbed by atmosphere. Of these 19 units, the 17 units they are absorbed by gases and 2 units by clouds. 17 units they are absorbed by the gases in the atmosphere, and 2 units they are absorbed by the clouds. Now, how much energy is left if we subtract this 19 from 66? Now we get 47 units it is transmitted through atmosphere on the earth. Out of these 47 units, we can see here that 23 units they are diffused radiation. Okay, so 23 units, they come as diffused radiation through clouds, diffuse radiation through clouds, while 19 units 19 units they are received as direct sunlight. Okay, direct sunlight, and 5 units 5 units as scattered radiation. Okay, so we got this 23 diffused, 5 units as scattered, and then 19 units as the direct sunlight. Scattered sunlight. So it is this 66 unit which is available on in the earth atmospheric system to heat up the atmosphere. So there is this 66 units which heats up the atmosphere, and it is also known as effective effective solar radiation. Okay, so basically we receive only 66% as the effective solar radiation on the earth. Now to maintain the heat balance, a similar amount of heat should be radiated back to the space. So if we look at this, the right hand side of this diagram, we saw here that of the 100 units, earth has only 66 units to heat up or to run its systems. Okay, but to maintain the heat balance, what needs to be done? Let us see that. I'll add one more slide to this. All right, now how much amount of energy is radiated back to these back by the earth? It's 120 units. So 120 units radiated by earth. Now where this 120 units come from? See, we had some amount of around 66 coming in, and then earth's internal heat, the long wave radiations which were converted on the earth, they all are now going back. Out of that, out of those 160, sorry, 120, 6 units, 6 unit, they directly get radiated back, directly radiated to space without any hindrance. They go back. How much is left now? 114 units, 114 units they are left. So this 114 units, it is absorbed by the atmosphere, absorbed by the atmosphere. Now what does atmosphere do? It's again a very tricky process. Of this 114 units, atmosphere retains 6 units, retained because of the gases. See, gases are very selective absorber. They do not absorb the entire amount of energy. They are very selective absorber. So retained by atmosphere. Also remember that not all gases absorb the heat in a similar way. Nitrogen has the least absorption quality, while oxygen, ozone and carbon dioxide, they absorb the gases in the best way possible. So they have the maximum absorption capacity. Out of this 114, 6 units are retained by atmosphere, and 108 units, it is re-radiated back to the earth, re-radiated back to the earth. Now 10 units, 10 units are lost to atmosphere, lost to atmosphere by turbulence, by convection, means wind activities, turbulence, convection, etc. 23 units, 23 units, they are lost to the atmosphere as latent heat in hydrological cycle, hydrological cycle. So when we say hydrological cycle, it includes evaporation. I'll show this diagram to you, just wait for a minute. Condensation and precipitation. And then, so what did we get? This, out of this 114 units which was absorbed by the atmosphere, plus this 10 units, plus this 23 units. So see here, in this case we can see that we have this Radiation from the land water surface is 120 units. Radiation to the earth is this 106 units. Now a total of this 100 114 units. Then in previous case there was this when the solar insolation was coming, the atmosphere had already absorbed 19 units. Okay, so how much is the total amount of units absorbed by the atmosphere? 114 plus 10 plus 23 plus this 19 also, because it was previously there in the atmosphere, plus 19. So this comes out to be 166 units, right? And out of this 166 units, how much did it radiate back to the earth? uh, Sorry guys, this will be 8 units. I just did some mistake and this will be 106. Yeah, okay. Now once we had this so just let me correct myself. Out of the 114 units absorbed by the atmosphere, 8 units are retained, 106 units are re-radiated back to the earth. This thing, this thing. So 10 units as sensible heat and turbulence in convection, and then there was latent heat of condensation. It caused the radiation of 23 units back to the atmosphere. So we had this 114, this 114, this 10, this 23, and this 19. It comes out to be 166 units. And out of this 166 units, 106 units was sent back to the earth. So the remaining is 60 units radiated back to space. Now when the light was uh, coming in, then what was the total amount which was sent back to the atmosphere? If you uh, see here carefully, then yeah, these 6 units, they were directly radiated to the space. So these 6 units were radiated from the earth's surface, and this 60 units, they were radiated from the atmosphere. So the total heat, total energy sent back in the space was 6 plus 60 is equal to 66 units. So we had a total of 66 units coming in, and we have a total of 66 units going out, which means that the heat budget is explained. Okay, this is called as the heat budget. Let me show this diagram to you again. Of the 100 units coming in, immediately 34 units, they are lost to the space. Now we have only 66 units which have to come on the earth. Of those 66 units, 19 units, they are absorbed in the atmosphere by clouds. Of those remaining 47 units, there are 23 units, 5 units, and 19 units which are there. Okay, so this is the 66 units. Of the returning 120 units from the earth, 6 units immediately goes into the space directly. Remaining 114, uh, out of those 114, 106 units are sent back to the earth, 8 units are absorbed. This 10 unit is by sensible heat, turbulence and convection, and 23 units by latent heat of condensation. And previously, in the previous case, if you remember, this 19 units was already absorbed by the atmospheric clouds. So we add this 4, 114, 10, 23 and 19, we get 166. Out of this 166, how much was coming back? 106. So we have 66 units of uh, heat available for heating up the earth and driving its processes, and 66 goes back to the space as long wave radiation. So this balances the uh, amount, this balances the budget. Okay, now this heat budget, it has variation according to the latitude. So if in this diagram you see the distribution according to the latitude, over here we have the north and south hemispheres, and if you see here carefully, there is a deficit and there is a surplus of this energy. The deficit of energy is beyond the tropics, so this is a tropical latitude. So from around 40 degree north to 40 degrees south, let me write it over here, 40 degree north to 40 degrees south, there is a surplus of heat, while going towards the higher latitudes from 40 degrees north and south, we get a deficit of uh, this heat. Now, as I have already explained to you previously, how the latitudinal distribution, the tilt of the earth, the angle of the sun's rays, the albedo, the scattering, diffusion, reflectivity, all these, they impact the uh, insolation received on the solar radiation or insolation. Now, if the this was the case, then tropics would have been always warmer, and the poles or the higher latitudes should have become progressively cooler. But this does not happen. It means that there is a transfer of heat transfer of heat from the tropics towards the higher latitudes. And how this transfer takes place, there are several media of transfer. Most important are the wind circulation. The wind carries the heat from the surplus zone towards the deficit zone. Then we have the ocean circulation as well, the ocean currents as well as the deep ocean circulation. They are very important sources of the transfer of heat from the surplus zone to the deficit zone. Okay, so we complete the first topic, the insulation and the heat budget. Sorry for that small mistake in between. So if you face any difficulties, any problems, uh, please do write me in the comment section, ask me questions, and I shall be very happy to answer those. Yes, you should, for the net examination, keep this diagram of latitudinal heat balance in mind. They can ask you several questions based on this. Then this diagram of albedo is very very important, how the variation of albedo takes. They may ask you that out of north and south poles, which pole has got the highest albedo. So if you see over here, the north pole has got lower albedo than the south pole. Can you guess the reason why? Can anybody guess the reason and write in the comment section why North Pole has lower albedo than the South Pole? Then you may get questions on this. Which of the following, they may give you the options, arrange the following according to increasing or decreasing albedo values. Okay, then this diagram is very important. There have been questions from this diagram in the previous year's net examinations. Okay guys, so we complete this topic, and I shall meet you soon in the with the next topic. Please, if you have any doubts with this calculation of incoming solar radiation and then radiation by the earth, then you can always you are always welcome to ask me the questions. Okay, all right, so I guess I aroused your interest in climatology. Do follow the book by DS Lal. That is enough for the net examination. Okay, you need not bother a lot about it. All right, till then, we meet the next. Do keep studying, keep on asking questions. Bye bye.